Hi pre-calc folks, we are working with vectors and getting a little bit further into what we can do with them and looking at the dot product and things that involve the dot product, the angle between the vectors, fun stuff like that. This is sort of an overview note sheet of some of the concepts we're going to use on these problems. I'm just going to work some example problems. I will reference this as I go, so I'll come back to this, but I thought you might want to see it right at the first of the video in case you want to reference it later. All right, first, find the dot product of u and v. Okay, the dot product of two vectors. It works so much like matrix multiplication, you're not going to believe it. It's pretty much just like multiplying matrices, multiplying a row times a column. Okay, so I have in many of these examples, I have gone ahead and written my vector as a linear combination of these unit vectors, I and j, because I just want to remind you that that's just the same as this. There it is in component form. Okay, so if I'm going to do the dot product of u and v, and it basically is written just like a dot for multiplication, it's kind of like saying I'm multiplying them. I am going to multiply first entry times first entry, and then say plus, and then second entry times second entry. And it's super simple because it's like the first entry of u times the first entry of v plus second entry of u times the second entry of v. It's super simple because with matrices, this goes on and on for a while, but with vectors, you're either going to have 2D vectors, excuse me, or 3D vectors where you'd have 3 entries. So the longest this would ever be is first times first, second times second, third times third. Here we only have 2D, excuse me, not v. And so 3 times negative 2 plus 2 times 1, and my answer is negative 6 plus 2, which is negative 4. And that's it. That's the dot product of those two vectors. So if I am finding the dot product of two vectors, it is going to be just one single constant, one number. Okay, looking at these are where it's like, let's get a little bit more involved. Let's do a little bit more operations. V times W dot product, that's negative 3 times 1 plus 4 times negative 4. So negative 3 times 1 is negative 3. 4 times negative 4 is negative 16. And I get negative 19. Again, the dot product gives me just a constant, just a number. Next, 4 times u. So that's doing scalar multiplication. 4 times 2. I started to write plus, sorry. Times, and this is a dot product, negative 3, 4. Excuse me. So first I have to go ahead and multiply 4 times each of these entries and get 8, 8. Now I'm doing the dot product of 8, 8 and negative 3, 4. So it's 8 times negative 3 plus 8 times 4. You could go ahead and say that's negative 24 plus 32, or I could factor out this is 8 times negative 3 plus 4, which is going to be 8 times 1. Just another way of looking at it. Finally, we have here the dot product of u and 2v, or twice v, and then the dot product really of all of that and w. It's actually not dot product actually. Let me restate that. Let's just see. Let me just show you what's going to happen. These two, I'm doing a dot product of two vectors, and the second vector is going to be 2 times v. When I do that, so 2 times twice this plus 2 times twice this, I'm going to get 2 times twice negative 3 plus 2 times twice 4. I'm going to get a single number. Okay, so this gives me what? Negative 12 plus 16 is 4. Then I'm multiplying, it's not a dot product because that's just a single constant. So I'm doing 4, all of this is 4. So it's 4w. So that's just a scalar multiple of a vector. So 4 times the vector 1, negative 4 is just 4, negative 16, and that's going to be a vector. All right, moving on. Use the dot product to find the magnitude of u. There's an example like this in your book, a really good example for this. And I say it's a really good example for this with the caveat that there is not a great example for this. They're just trying to make you recognize a relationship here. And that is, if I want to find the magnitude, let's look at finding the magnitude of u. Well, remember u, this is the same as 6, negative 10. Okay, so the magnitude of u is square root of 6 squared plus negative 10 squared. So that's the square root of 36 plus 100, which is the square root of 136. Okay, now, the way they're saying, hey, use the dot product is if I were to, instead of finding the magnitude the normal way, what if I said, I'm going to find the dot product of u and u? Okay, in other words, that's the dot product of 6, negative 10, and 6, negative 10. So in other words, 6 times 6, which is 6 squared, plus negative 10 times negative 10, which is negative 10 squared, which is, notice the numbers, 36 plus 100, which is 136. That is the dot product of u and itself, or you could say u squared. Okay, so what they're pointing out here is that the dot product of u and itself is the square of the magnitude. So if I take the square root of that dot product, I get the same thing as what I did for the magnitude. So the dot product is the square of the magnitude. It's just an observation they want you to make here. It may come back to haunt you later. Example 4, find the angle between the vectors. Okay, here's another fun new thing we're doing. The nice thing is, there's a formula to find the angle between two vectors. Here's what we do. Now it looks a lot weirder and or more complicated since we haven't worked with these than it really is. All this says is find the dot product on top, and on the bottom we're dividing by the product of the magnitudes. Okay, so in order to do this, there's basically 3 things I need to do. I need to find the magnitude of u, find the magnitude of v, and find the dot product. And I do have to multiply these, but that's not really as much a vector operation as it is just plain old math. So this one is in component form 2, negative 3. This one is in component form 1, negative 2. And I need to find the, remember, here's the formula. I need to find the magnitude of u. I need to find the magnitude of v. I need to find the product of those two things. And I need to find the dot product of u and v. And then I can just put this on top of this and say that's the cosine of theta. Now what am I going to have to do there? You might want to think ahead there, but let's go ahead and dive in. Magnitude of u is square root of 2 squared plus negative 3 squared, which is the same as 3 squared. 4 plus 9, square root of 13. Magnitude of v, square root of 1 squared plus 2 squared, or negative 2 squared. And that's 1 plus 4, square root of 5. So when I multiply those two, I get 13 times 5. 13 times 5 is 65. So that's going to be my denominator. Then the dot product of these two, 2 times 1 plus negative 3 times negative 2. So 2 times 1 plus negative 3 times negative 2 is 2 plus 6, which is 8. So cosine of theta equals the dot product goes on top, and the product of those two magnitudes goes on the bottom. So this is what I get. Well, if that's the cosine of theta, then theta will be the inverse cosine of that. And there's really no reason to rationalize it right now because it's going to go in your calculator. So let me grab a calculator here. There we go. Inverse cosine of 8 divided by root 65. It's a lot like root 66 there. And I get that the angle between these two, let me just check that I am in degrees. It's kind of weird looking, but I'm going to have some faith here, is about 7.13 degrees. And that's my answer. All right, next. Related, find the interior angles of the triangle. Well, let's look at that. -3, 0, right here. 2, 2, right up here. 1, -5, down here somewhere. Basically, think of each of the sides of the triangle as a vector, and what you're doing is you're finding the angle between two vectors, the angle between the two vectors, the angle between the two vectors. So what we have to do for each one of these sides is find the, it doesn't matter if it's component form or any other form, but find the vector that represents it. So from -3 to 2, this is 5. And from 0 to 2, that's 2. Okay, this one here is from 1 to 2, that's 1. And from -5 to 2 is 7. And over here we have from -3 to 1, that's 4. And from -5 to 0 is, or 0 to -5, let's just do it that way. It's -5. So we're finding the angle between this and this, just like we did in example 4. Same exact thing that we just did here. Angle between two vectors. Between these two and between these two. And do we have to go on? Or is there another way to find the third angle? Think about it. Okay, we're pretty close to the end here, but unfortunately, I'm afraid we're about to get interrupted by a custodian with a vacuum. So we'll see how that works. I may have to come back and tell you then. Okay, find the dot product of u and v, where theta is the angle between u and v. Well, look at how many things we have here that are familiar from this formula. So what I'm going to do is I'm going to plug those things into this formula and see what happens. So cosine of pi over 3 equals dot product of u and v over magnitude of u times magnitude of v. So that's 4 times 12, which is 48. So in other words, using the formula, I could get the dot product of u and v by multiplying 48 times cosine of pi over 3. Let me give you a helpful hint. This just is going to go in your calculator. That's all you have to do. But this is in radians. So you have to go to mode in your calculator and change it to radians instead of degrees. So look for where it says DEG and RAD and change that in the calculator and in the mode of the calculator. All right, last but not least, you're going to be asked, are these two vectors orthogonal, parallel, or neither? What the heck is orthogonal? Orthogonal is the word we use that means perpendicular when we're talking about vectors. It's really all it means, is perpendicular. How do I tell if two vectors are orthogonal? I find their dot product, and if I get 0, then yes, they are. So let's see. This is 8, 4. This is -3, -6. And I'm going to get the dot product of those two to see if these two vectors are perpendicular or orthogonal. 8 times -3 plus 4 times -6, which is -24 plus -24. If this had only been a positive 6, then we would have been yes. But this is a no, not orthogonal. Parallel. To me, the easiest way to see if they're parallel, and I'm going to come down here, is to draw them and think about slope. 8 right and 4 up. That's what 8, 4 is. So it looks like this. Okay? So change in y over change in x, this has a slope of 4 over 8, or 1/2. Remember, things that are parallel have the same slope. -3, -6. Can you tell right now? -3, -6, this is not going to have the same slope necessarily. Well, it's not going to have the exact same slope. But let's keep looking. This is -3. This is -6. Actually, it might, come to think of it. What I was pointing out is it's not in the same direction. Okay, it's not in the same direction, it's in the opposite direction. But we're just looking at, are they slanted the same? So slope is change in y over change in x. This has a slope of 2. This one has a slope of 1/2. The slopes aren't the same, so no, because we have different slopes. Neither means yep, because we just ruled out the other two, so it has to be neither. And that will get you a great start, if not even finished. It might even get you all the way through your last assignment. Well, not last assignment ever, but out of this set. See you tomorrow.